we define colligative properties as being properties of solutions that depend only on the concentration of solute particles and not on their identity. In one of these here you worked with in lab already this semester. And the one that you worked with was one where you added a whole bunch of different things to snow. You added some salt to snow, you added some ice melt to snow, you added some sugar to snow. In each case, once you added those solutes, what happened to the temperature of that snow? Do you remember? Temperature went down. Temperature went down. And we call that colligative property, and it didn't matter which stuff you added, the temperature went down in every case. We call that colligative property freezing point depression. In one of the uses of freezing point depression, what is one application of freezing point depression?
Getting rid of snow.
Getting rid of snow where?
On the roads.
On the roads,
Ways.
sidewalks, whatever else, yes. We also use it in our cars when we put in antifreeze. Put the antifreeze into our radiators, and that keeps our engines or radiators from freezing up in the winters. Now the second one pertains to our answer to this last question, and let's see what you guessed here. Oh, we're not going to do that yet. We're going to demo it. And remember now, the water is not boiling at 100 degrees Celsius because?
The atmospheric pressure.
The atmospheric pressure, right. The atmospheric pressure is something that will change, and so it depends upon what that atmospheric pressure is. And so we've had this boiling here for several minutes, and now I just adjusted it a bit here to kind of get this consistent, but what I'm going to do is I'm going to go ahead and add some salt to this, and we're going to see what happens to this boiling point. We've got about 100 milliliters of water, and watch now how much salt I dump in. So we're dumping in a whole lot of salt into only 100 milliliters of water. We're going to get this all to mix up, and we're going to see what happens once it returns to a boil. And once we do that, then we're going to have a name for this one. It's going to be called boiling point something. And we should see here now what's happening to that boiling point. Looks like that boiling point will have increased. And so let's check to see what we guessed. And we see that the boiling point of that solution is actually greater than. So we call this phenomenon boiling point elevation. Now, one of the ways we make use of this is how? Well, remember that antifreeze in the car. In the winter, it keeps the radiator and engine from freezing up, and in the summer, it will prevent it from boiling over. Because it raises the boiling point in the summer, it lowers the freezing point in the winter. And marketing has done a great job of this, because in the winter, they try to sell you something called antifreeze. In the summer, they try to sell you something called coolant. And guess what? It's the same stuff. It's the same stuff. Antifreeze and coolant. It's the same stuff. So again, it prevents it from freezing in the winter, prevents it from boiling over in the summer. And don't say cooking. And that's one of the things that many will say. Oh yeah, my mom used to say that you add some salt to water, and she does that. Now, okay, don't be sexist, because I was the cook in my house, okay? I didn't add salt to my water, and the reason why? It doesn't do any good, okay? If anyone ever adds salt to the water, it's not doing anything except maybe give it a little bit of taste. It doesn't make it boil any faster, doesn't make it boil any higher, because if you look, remember I used about 100 mils of water and how much salt?
Lots of salt.
A lot of salt. And if anybody ever adds salt to your water, you have a big pot of water, and what do? Little pinch of salt. A little pinch of salt in a big pot isn't going to do anything when, in order to get this to change by, what, about 3 degrees, I only had 100 mils of water and a whole bunch of salt. So that little pinch isn't going to do a thing. That's just a wives' tale. If it does anything, it adds a tad of flavor. But even then, the amount that's added is so small that it really doesn't have an effect. So tell your mom or dad, or whoever's the cook, it's useless. Don't bother. All right. Then a third one we have is vapor pressure depression. Vapor pressure depression. And we're not going to look at that one. We'll just mention it. But the one that we are going to look at is the last one, which is osmotic pressure elevation. Osmotic pressure elevation. Now this colligative property is related a whole lot to the extra credit lab that many of you just completed. And it worked something like this. This one was performed over a period of 3 days. So put down day 1, day 2, and day 3. Now, first one here contains vinegar in day 1. Day 2 contained corn syrup. And day 3 contained water. And for those that didn't do it, here's what was done with the eggs on those days. On day 1, into the vinegar, we placed an egg in its shell, a raw egg in its shell. So a raw egg in its shell went in day 1, and what happens to the shell? Shell dissolves. So the idea then was to dissolve the shell in this first one. Once the shell dissolves, we then take the egg out of here, we put it into the corn syrup. And what happened to the egg on day 2? Shrunk up. So it kind of looked like a deflated football I often hear. And then what we did there is we took it out of there and we put it into the water. And once we put it in the water, what happened to the egg? Which is what you have up here. The egg grew back. In fact, it probably grew back even bigger than what it started with. So the egg was huge. I probably exaggerated the size here in this first one. It's probably more like about this. So we explain this in terms of osmosis. And in osmosis, we define like this. And here's how chemists define them. We define it a little bit differently than biologists, but it's the same idea. We define it as being the movement of water through a semi-permeable membrane, and biologists will finish it like this. They'll say from areas of high concentration to areas of low concentration. Chemists, though, say it like this. We say that it is from areas of low solute concentration to areas of high solute concentration. Biologists simply use the word concentration, but what they're really referring to is the concentration of the water. But when chemists talk about concentration, we always talk about it in terms of the solute. So what happens here in the egg is this. Once we put it into the corn syrup is really highly concentrated. So what's happening to the water here is the water is moving out of the egg. And as the water is moving out of the egg into the corn syrup, where the corn syrup is more concentrated, that causes that egg to shrivel up. And then when we take that egg out of the corn syrup and put it in the water, the area of higher solute concentration is on the inside of the egg. So the egg gets bigger because water is moving into the egg. As it moves into the egg, then the egg winds up growing. Now, some applications of this. There's 2 of them, and we're going to run over about 1 minute. I apologize. So, a couple applications. One of these. Any of you planning careers in the health professions. Doctor, nurse, PT, whatever. Okay, so if you're planning a health career profession, let's say that you want to administer a drug like morphine to someone. Okay, you can't just, if it's going to be in an IV solution, you don't just put the morphine into a bag of water and hook that bag of water up to someone, because if you hook that morphine up and put that morphine into a bag of water, that bag, IV bag, is still basically water. And what's going to happen then, if it's mostly water, it's going to come into contact. If you think of this now not as an egg, but as a red blood cell, what's going to happen is that water is going to wind up rushing into those cells. When it rushes into those cells are going to swell up, and in many cases those cells will burst. And so we can't do that. So what's done then is that when you administer a drug like morphine intravenously, you wind up dissolving it into something like either a glucose solution or a saline solution. If it's glucose, it's a very specific glucose solution. It's going to be 5.5%. If you put it into saline, you're going to put it into a 0.92% salt solution. And the reason why those are picked is because those have the same concentration as the stuff that's in your fluids in your body. And so, again, you put them in there. If you wear contacts, you don't clean your contacts with water. You clean them with saline solution because you don't want your eyes to hurt. You want to make sure that they stay the same. And so you don't have any water moving in or out. The other application deals with what's called reverse osmosis. Anybody know what reverse osmosis is used for? Some of you even use it in here. We use it to purify water. And in fact, many say that this is the water purification system of the future. And what happens here then is that if this is a pipe, what happens then is you put a membrane inside that pipe. This here is that membrane. Semi-permeable. The term semi-permeable means it allows some things through but not others. And so what happens is that, let's say that we had pure water over here, and we had our impure water over here. Following our definition of osmosis, if this is pure water and this is impure water, which direction would that water want to move? Is it going to want to go that way, or is it going to want to go to the left? Well, it's going to want to go to the left, because it always goes in the direction of the higher solute concentration. Okay, that's the direction that osmosis would put it. Well, if we want pure water, that's not good. So what we do then is we hook this up to pumps, or we build water towers like Coon Rapids or all towns have. We build a big water tower which has enough pressure, a pump. We just push it with enough pressure such that it is stronger than the osmotic pressure, and we push it in the opposite direction that osmosis intends to take it. And that's why it's called reverse osmosis, because we're pushing it against osmosis. And then we do that, we get the pure water that comes out the other side.